in this part of the homework, I'm going to describe and show, while deriving, why our liquid is, why in a closed system such as this, that our solution, whatever it is equally as happy being a solid, that's not solid, equally as happy as being a liquid as it is being a vapor. So first, we're going to have to create a few just redundancies. For example, saying NV, the moles of the vapor plus the moles of the liquid equal N. And also stating that the derivative of N equals 0. And then another thing we have to state is that, let's see, yes, dNL equals negative dNV. And what this is stating is that whenever, if this were to increase, so if GV is ever to, or this, if the vapor phase is ever going to gain 1 mole, that means the volume, or not the volume, the liquid phase is going to lose a mole. And so it's really just saying it's hand in hand in a closed system with a set temperature and a set pressure. And so now we can set up an equation in which we can have, let's see, and it would be GV times NV. Then we're going to add, let's see, NLGL, NLGL. And that would equal our total energy, otherwise known as our Gn, which we know is 0 because the derivative of n would be 0. So now we're going to derive, in which you're going to do the product rule twice. So over here, we would have, let's see, we would have GV, oh gosh, it looks like a 6. I've written so much on this chalkboard today, it's just covering everything. That would be dGV times NV plus dNV times GV plus, now we're going to do the exact same thing on the other side, so except changing the V's for L's. So dGL times NV, NV, NL, plus, this will be, let's see, NL, as we took the derivative of the GL, now it's going to be dNL times GL. Oh my gosh, I can't get writing this down for the hang of it. GL. And that, as we know, equals 0. So what we're going to do now is we are going to separate our variables. So we know that, let's see, I'm just looking at something real quick. Yeah, I think we could do GV, because we can plug this in right here. And so instead of DNL, we can use, so this is, so we do, because we can change one of the DNVs into a negative, we gotta get GV minus GL, all right? And then we're gonna take that to the D. So you would have dGV times NVT, or times NV, plus DNV. We would get DNV times GV plus GL. And then if we have DNV over here, that would take care of this. Then we would have plus dGV times NVT. And then we're also going to add, let's see, where's this? So we're going to add these two. And then we're going to add dGL times NL times NL. This shouldn't be a T. I just keep mixing up my pluses. But for the reason we're taking dGL and dGV over here and not putting it into this function is because we know that if we're at constant, or for the derivative of G, it equals S times the change in temperature plus volume times the change in pressure. And if this is a closed system, the temperature and the pressure are going to be constant, which means this term is 0 and this term is 0, which again will give us dNV of GV minus GL, and that equals 0, which will give us that GV equals GL. Otherwise saying that the Gibbs energy is the reason that any of our molecules are equally as happy to be in their liquid phase as they are in their gaseous phase. And we've always wondered why they're just very compatible, and why they're okay with not separating into one another if they're held at a constant T and constant P. And the answer is because their Gibbs energy are the same, which is very mind-boggling when you first think of it. But if you slowly start looking at the equations and start diving in more, it makes a little bit more sense. Now that we've shown why using Gibbs energy, why a substance is equally as happy in its liquid phase as it is in its vapor phase, we are going to derive Clausius-Clapeyron's famous expression. And so first, we're going to start off with GV equals GL, just stating the Gibbs energies are equal. Then we're going to say dGV equals dGL. And we have an expression for that. The expression is going to be, it's right over here, negative S vapor phase times dT plus V vapor phase dP equals negative S liquid phase dt plus V liquid phase dP. And when you factor this all out, not factor, you start to move all of the different things to the right place, you get SV minus SL dt equals VV minus VL dP. And to get the derivatives on the same side, we end up getting SV minus SL over VV minus VL equals dP over dt. And we also have an expression for when we have dt, as it also it's also important as it refers to ds as well, and that is dH equals TdS, and then it's going to be plus VdP. And this is important as in Clausius-Clapeyron, right now we are going to say that the change in pressure is 0, or at least very minimal. And so that means we can rewrite our equation as ds equals dH over T. And this is important because if the change in S, otherwise known as ds, right here, also known as SV minus SL, also known as the enthalpy, the enthalpy of vaporization. So we can write this as delta T, delta H over T, right? And then we're going to VV minus VL. And something important because Clausius starts stating that the pressure and all that, but Clapeyron is who states for an ideal gas, which is important because for an ideal gas, the volume of the vapor phase is about 1,000 times larger than the volume of a liquid phase, which means we can kind of leave him alone and technically state that it's 0. So we can end up writing that delta H over T VV, right, equals dP over dt. And we know for volume, using our illustrious curve here, that this ends up equaling, I gotta go over here, we have delta H times P all over T squared times R. Oh, geez. And that equals dP over dt. And now we are going to transfer transfer the derivatives over and across, as H and R are constants. And so what you end up getting, let's see, this one's a little little bit bigger, is you'll end up getting 1 over t squared dt, derivative, and then that equals, that's the integral, holy crap. Wait, we want to integral it, sorry, to get rid of the dt, and that equals delta h times, or over r, oh, I switched the sides up, excuse me. Yeah, I switched the sides up, that's on me. Yeah, so it's going to be, along with this, it's going to be delta h over r times the integral of 1 over t squared dt, which then equals, we're going to transfer p over to the other side, so it's going to be dp over p, the integral. So we will end up getting, on this side, the ln of p1, p2 over p1, in which over here we end up getting negative h. I'm trying to make sure everyone can see. I'll go over here. Negative delta h over r. Okay, you can see. And then with 1t, that makes this negative. That's why we have it here. And then we have 1 over t2 minus 1 over t1. However, with this negative, we can change this sign, or we can switch these around. So over here, I'll write our final Clausius-Clapeyron expression, in which we get delta h over r times 1 over t1 minus 1 over t2 equals the natural log of p2 over p1. And that is Clausius-Clapeyron's expression.